Yes, we are now going online on YouTube as well. Okay, I think we can start. Well, hello everyone, and welcome to another talk in our webinar series. This webinar is also being streamed live on YouTube, and you can find the link on our website, or you can access it on our YouTube channel, LIneA MCTI. Today, we are very happy to have Dr. David Latham from the Harvard-Smithsonian Center for Astrophysics, and he will talk about the transiting exoplanet survey satellite. Dr. Latham, thank you very much for being with us today, and the floor is yours.
Thank you, Rodrigo. So I'm going to talk about TESS and the search for rocky planets. We're now at a pretty special time in the history of astronomy where we are finding enough rocky planets transiting nearby stars that we can begin to characterize them in some detail. So I'm not talking about gas giant planets with extended envelopes of hydrogen and helium. Well, they're almost too easy because they're big and it's not that difficult to characterize their atmospheres, for example. But instead, I'm talking about small terrestrial planets with rocky surfaces and probably compact secondary atmospheres. The original hydrogen and helium are gone, and the atmospheres are mostly heavier molecules, things like water and carbon dioxide. And we're especially interested in rocky planets that are the right distance from their host star for water to be liquid on the surface, and enough like the Earth that we can imagine that life as we know it could be comfortable there. Of course, we haven't ruled out the possibility of a rocky moon orbiting a giant planet if it's at the right distance from its host star. That could be potentially habitable. But so far, we have not identified any Pandoras. So our dream, my dream, a lot of our dreams to detect biomarkers in the atmospheres of rocky exoplanets using remote sensing. I like to say we are going to look for evidence that life has polluted its environment. And that might be in the form of oxygen in the atmosphere, although there are other non-organic ways to make oxygen, so it may not be the best indicator that the pollution has come from life. But there might be other molecules that old Mother Nature hasn't figured out how to make. And so I will tell you about why transiting planets are so important contributing to this effort. As you know, astronomers have developed two nice ways to find exoplanets. Both of them are indirect. For quite some time, the radial velocity technique, where we look for the orbit of the host star around its center of mass with a very distant, unseen planet in a much wider orbit. In fact, in many cases, the center of mass is inside the surface of the star because the mass ratio is 1,000 to 1 or 10,000 to 1. And there is a fundamental limit to what you can do with Doppler method. And that's because we don't have the orientation of the orbit. If it's edge on, you get the full projected velocity along the line of sight. But if the orbit is face on, then the velocity of the orbital motion along the line of sight is can be quite small, and you don't know whether you got a low mass planet or a nearly face-on orbit. And then there's the transit method that has been very successful in the last 20 years, where we watch for light from the star to change, to have a little dip as a dark planet passes in front. And the area of the star that is blocked by the planet tells us about the size of the planet compared to the star. So this is a way of getting the planet diameter. Of course, it's relative to the star, and also the Doppler method is relative to the mass of the host star. So in both these cases, you need to know something about stellar properties. I sometimes like to say stellar astronomers are useful again because planets orbit stars, especially stellar spectroscopists, to help get the spectroscopic parameters of stars. But most importantly, from the point of view of this talk, the transit method gives the orbital inclination. The orbit's close to edge on. Actually, you can get it very accurately from you can get the inclination very accurately from the shape of the transit. And that removes this inclination ambiguity, the sin I implication. It's not just a minimum mass. You get the actual mass from the Doppler orbit. And that gives you really interesting information. For example, mass and radius means you can calculate the bulk density, and you can, with the help of models, say something about composition and structure. Have you got a gas giant like a Jupiter or a Saturn, or an ice giant like Uranus and Neptune, or a rocky planet like the terrestrial planets in our own solar system, or maybe things that we don't have in our own solar system, water worlds, or planets between the size of the Earth and the size and mass of Uranus and Neptune. And I wanted to point out the importance of also getting the surface gravity, because when we go to characterize the atmospheres of transiting planets, we're looking for very small changes in the apparent size of the planet as it transits the star. And therefore, the depth of the transit changes. And that's changing depth with wavelength, which is telling us about the absorption, for example, due to molecules in the atmosphere. And surface gravity goes into the mean molecular weight and therefore the scale height of the atmosphere. So hydrogen and helium atmospheres are much larger scale heights, and the atmosphere we're most interested in would be the secondary atmosphere of massive molecules will be much smaller. So I'm going to tell you a little bit about my history with transiting surveys, photometric surveys for transiting planets. I'm not going to talk anything about the early work with ground-based surveys. Those were important, or about the pioneering CoRoT mission led by the French, because the real breakthrough came with the Kepler mission, launched in March 2009, a spectacular nighttime launch on a Delta Heavy 9 strap-on Delta. And here's the field of view on the left panel, just 100 square degrees roughly, very near the galactic plane in the constellation of Cygnus and Lyra. And the concept of Kepler was to look for true twins of the Earth, transiting Earth-like planets in an orbit like the Earth around the sun at a 1 year period, and radius as small as the Earth. And that meant we had to look for at least 3 or 4 years in order to see more than one event. And so we were going to stare at this one field of view at about 150,000 sun-like stars, which meant we had to go pretty faint. And the orbit was great, an Earth trailing orbit for stability, get away from the low Earth orbit thermal environment of day-night cycles, and get good continuous light curves. So here is perhaps the most important impact of the Kepler mission. It's not the final draft, final version, but an earlier version of this diagram, because it's not quite so cluttered. And it's got orbital period along the x-axis. So there's 1 day over at the left edge and 1 year over at the right edge, and size relative to the Earth. So the Earth is this one line, and you notice there are essentially no true Earth twins in this diagram. Just hadn't gone long enough and had good enough sensitivity to push into that, although the original extended mission was going to do that. We were approved for an extended mission after the first 4 years. And up here you have things the size of Jupiter. And these were the planets that we were finding with the ground-based photometric surveys and that the CORO mission was finding. And then hidden was this enormous population of planets unlike anything in the solar system. You know, Uranus and Neptune are 4 Earth radii, and the Earth is 1. And all of these planets are in orbits around other stars, but not in our solar system. Pretty amazing. And furthermore, very often there are 2 or 3 transiting planets, or even more, up to 6 in this diagram, transiting the same host star, which means that they're all lying pretty much in the same orbital plane. The systems are very flat, even flatter than the solar system. So this is the poster child of that result, Kepler 11, with 6 planets with periods between 10 and 118 days, and all of them transit. And you see 118 days isn't much more than the period of Mercury. So very compact, in many cases, full systems, very little extra room for other planets that didn't transit. So the 2 legacies of Kepler that were that planets smaller than 4 Earth radii orbiting close to their host stars were common. Most stars host at least 1. And compact systems of multiple small planets orbiting in the same plane are also very common. All right, let's go back to this diagram because I want to now to look at the relative occurrence rates of planets as a function of radius. So we're going to make a histogram by collapsing the population onto the vertical axis, the y-axis. And several people did that. One of the first efforts was carried out by Francois Fressin, published in 2013. Here you now see radius. It's a logarithmic scale. So here at 4 Earth radii, that's the size of Neptune. And see already at the planets the size of Neptune and Uranus, the frequency has dropped off. The large planets are really much rarer than these small planets, smaller than Neptune. 15% for periods shorter than 85 days. This diagram has been corrected for the dependence of the occurrence of transits on the orientation of the orbit. You know, that's a big selection effect. The orbit has to be by accident very accurately lined up with the line of sight to the observer. And this diagram was based on stellar parameters from the Kepler input catalog. And that was a catalog that we put together using heavily relying on modest resolution photometry, medium band photometry. And so the stellar parameters, for example, the radius of the host star in particular, was not very well determined because photometry is not the best way to get a radius. This is before Gaia. This is too faint. Most of these targets, almost all these targets aren't in the Hipparchus catalog because they're too distant. And so the diagram got poor resolution on the horizontal scale. And one of the main efforts for following up the Kepler planets was to do better spectroscopy, to get better parameters for the host stars, to improve the resolution along the horizontal axis of the radius of the planet. And here is a very nice example of applying the new stellar spectroscopy, in this case, the thesis of B.J. Fulton, won a Templar Prize, by the way, where a couple of thousand high-res spectra from Keck were used to derive better stellar parameters and improve the uncertainty on the horizontal axis, and revealed this bimodal distribution, sometimes called the radius valley. So larger planets up around 2.5 Earth radii are common, and smaller planets as you push below 1.5 Earth radii down towards the size of the Earth. It's incomplete down here at the lower edge. A second distribution. And it's very tempting to wonder if that isn't the result of a transition from sub-Neptunes with extended envelopes of hydrogen and helium and other volatile gases, dividing it from the terrestrial planets, the two rocky planets where the atmospheres are very compact and therefore they don't make the planet look big. The atmospheres have very small scale heights because they're secondary atmospheres of massive molecules. So this diagram, I'm showing it because it's a modern diagram. It takes advantage of the fact that we now have Gaia DR2, we have parallaxes, we can get much better radii. And in fact, in this diagram, the limit is no longer set by how well we understand the stellar parameters. It's set by how well we measure the size of the planet from the transit depths and modeling compared to the star. And so the question is, are all the planets smaller than something like 2 or 1.8 Earth radii, are they all rocky? Is this the transition we're seeing here? Because this is radius. We got to have masses. All right, well, I'm in the business of measuring masses. So I'm going to show you something about how we address the challenge of getting masses for the Kepler planets, and then now for the TESS planets. So here's a plot over, oh my goodness, almost 3 decades for the masses measured for almost entirely unseen companions due to the Doppler effect. Starting back in 1989, HD 114762. A lot of these are minimum masses before we had transiting planets, which came initially in 2000. And so all of the ones in here are just minimum masses. But the thing I want you to notice is how the technology and the procedures improved with time, and the limiting mass that we could determine reliably got better and better, almost like a Moore's law. Look at this, log scale over on the left for mass or minimum mass, 1, 2, 3, more than 3 orders of magnitude improvement. But then, kind of like Moore's law, we hit the bottom. I haven't even bothered to plot what's happening over here, since there's been not a lot of progress since 2015 until quite recently, when there's a new generation of instruments that are able to do considerably better than meter per second velocity precision. Typical specs now are 30 centimeters or 40 centimeters per second. NEWIT, I saw from a meeting earlier this week, is now going to go online for scientific use in the next semester for 30 nights, still in commissioning. So why did things bottom out if we had pretty good precision? And the reason is, I'll get to in a minute, because I wanted to explain why we worked hard to initiate a project to give capability in the Northern Hemisphere to do very precise radial velocity work. The state of the art at the launch of Kepler in 2019 was HARPS in the Southern Hemisphere, but it couldn't look at the Kepler field of view because that was in the northern sky. And so in 2015, I consulted with my friend Michel Mayor from Geneva because we anticipated already in 2005 that we were going to need more capability for measuring very small masses for orbiting companions. And we set up a collaboration between Geneva and the Harvard University Origins of Life Initiative, which was generously funded by Harvard University as a new initiative. And also the Center for Astrophysics, we made significant contributions as well. And that would bring a new version of the original HARPS to the Northern Hemisphere on La Palma at Roque de los Muchachos Observatory. But then in 2008, the big recession put Harvard funding on a hold. And it took a couple of years for us to kind of climb out of that hole. And Francesco Pepe and I, who had taken over from Michel, because in Switzerland, they make you retire at 65. Isn't that ridiculous? So Francesco and I went on a tour talking to people about getting involved, and we started up a new collaboration and a new host with the Italians on the Telescopio Nazionale Galileo. And 2 years later, science operations started. The agreement was we got 80 nights a year, and CFA was responsible for Kepler and then eventually K2 follow-up after the second of the 4 reaction wheels failed and we could only look at the ecliptic with K2. Actually, it was a great thing. We got to look at new areas on the sky, 18 other fields of view instead of just that one field of view. But we weren't able to do the extended mission in the original field of view because that required at least 3 reaction wheels. And Geneva was interested in looking at really bright solar type stars and seeing how far they could push the mass determination limit. And then in 2015, we installed a solar telescope to feed the HARPS North spectrograph every sunny day when there weren't clouds. And then in 2017, we extended the collaboration for another 5 years, and we're beginning discussions now what we're going to do in 2022, hopefully go for another 5 years. So why did we install the solar telescope? Well, it turned out lessons that learned. Oh, I have to show you the spectrograph. You see, one of the secrets for getting really precise radial velocities is ultimate stability. So it's inside a vacuum chamber, carefully temperature controlled vacuum chamber, inside a room that's carefully temperature controlled, inside the coude area. And nobody is ever allowed to go inside and touch the spectrograph. Well, but I had Francesco take a picture of me touching it during commissioning in, let's see, it was late March 2012. But I need to get on, oh, what happened? I'm missing a slide here. Let's go back. Oh, we'll get to it. The solar telescope is important because it turns out the limit to our ability to measure low amplitude orbits is largely set by what many people call velocity jitter or stellar jitter in stars of a few meters per second. In the case of the sun, it's more like 4 meters per second peak to peak. And you have to get rid of that by a factor of an order of magnitude or something to push below the 1 meter per second orbital amplitude. So I want to introduce you to a diagram that you'll see several times in this talk, and that is radius, one of the observables from the Kepler mission and now the TESS mission, versus mass, which with the Doppler method comes from spectroscopic observations with largish telescopes of the radial velocities. And we really need precise masses and radii if we want to understand something about the composition and structure of planets. If we want to separate rocky planets like the Earth line here with 30% or so iron core and then a total rocky outer region, we want to separate that from like Uranus and Neptune up here. We have to worry about if there are other volatile elements. Is this population of planets between the Earth and Neptune that we don't see in the solar system? They could be made of planets that have a strong contribution from water, or they could have extended envelopes. And it doesn't take very much of a hydrogen and helium envelope to make the size of the star look bigger. You see, here's only 0.1% envelope and 2% envelope up in here. So you have this region of where things are degenerate. You're not quite sure how to interpret the radius, even when you do have the mass. And you really want to have precision in the mass on the order of something like 10%, otherwise you get too much of a spread on this axis, and you need the radius to better than that. If you think about it, if you're going to use bulk density to say something about what structure you have to the planet and what composition, then it's 3 times more sensitive, right? It's density's mass over r squared. So getting really accurate radii is important. And that's one of the things that the KOPS mission is designed to do and is doing now. So these models, I should acknowledge, are by Li Zeng, and the plots by Sam Quinn. And we want to know if we're separating things from these other lines. And there's just not enough really precise masses to do that. If you look at all the masses that are better than 3 sigma from Kepler and K2, just from Kepler and K2, you see there's a really significant contribution, but the precision of the mass measurements is limited largely because many of the targets from the Kepler mission were faint because they had to be so far away to get a large enough number for the primary motive of the mission. So do you see the radius valley? It's between 2 and 1.5 radii, so it's here. You can almost see the radius valley in here. But I prefer to think that if you are going to attribute the radius valley as a transition between rocky planets and planets with more volatile elements, you really need to be able to say whether they lie on either side of a line that actually is curved and has a slope in this diagram. Is it mostly closer to the Earth line or more closely to these things that have perhaps envelopes of hydrogen, helium, or perhaps more volatile elements interior like water in different forms? You know, water comes in many, many different forms. And I do need to acknowledge something that we didn't anticipate when we wrote the science section for the Kepler mission, that there were going to be so many flat systems with multiply transiting planets, which could interact, and from their perturbations, which give rise to transit time variations, we could figure out the mass ratios between neighboring planets. That's a technique that tends to work better for longer period systems where the time delays have more time to build up. So TTV masses from Kepler and K2 look like this, and you notice the colors are different. That's because they're in wider orbits, they tend to be cooler. You go back to the previous plot, you see that there's this concentration of hot colors. So these are systems where one of the early ideas, an obvious idea, is that the irradiation from the host star was photo-evaporating, driving off the atmospheres of hydrogen and helium. Then you get up to the cooler ones that have retained some of those envelopes. Ooh, Kepler 78 right there, one of my favorites. And we look at Kepler and try to evaluate its impact. I think we have to look at its unfulfilled promise. We didn't find any true Earth twins, no confirmed rocky planets in one-year orbits with a measured mass around a star like the sun, where water might be liquid on the surface, which is one of the strong goals we tried to make in the science section. And the real problem was that velocity jitter in quiet stars at the meter per second level and more is what is limiting the ability to work with those fainter systems that we were observing for follow-up for radio velocities from the Kepler mission. So lessons learned, well, a lot of lessons learned from the Kepler mission, but one of them is that correcting for stellar jitter is the main challenge in getting planets as small as the Earth. And you can make some progress correcting for activity using spectroscopic activity indicators, calcium-2 emission, H-alpha, things like that. Those correlations kind of work, but not very well. You can try to model the variations in the velocities due to activity using Gaussian processes. That has found a lot of applications, and it kind of works. But one of the things you learn is that you need intense campaigns of radio velocity work, often over consecutive nights, because you have to get your velocities in time periods short compared to the rotation period or the activity cycle period of the star. And so that's one of the things that you'll see in recent work. People organize the campaigns to try to avoid periods that are influenced by activity cycles. And missing planets, if there are gaps between transiting planets or outside transiting planets, extra planets in the system can distort the results, and you have to keep observing. And that's why we built the solar telescope. Solar observations are revealing. For one thing, they helped us understand the instrument performance on HARPS North. For another thing, you can look for spectral lines in your optical spectra that are less sensitive to activity. That's actually turned out to be moderately effective. Very careful selection of the lines that you use in your radio velocity measurements. So here is the solar telescope. And it's mounted up on the side of the TNG. And during the day, we look at the sun. And there's this little telescope, little lens right there with a Perspex dome for the weather, which you have to clean from time to time. And the sun is bright, and so you can build a feed into the HARPS North spectrograph using integration spheres and so on that make the sun look as if it's being observed as a star. Well, up to a point, because the sun does cover a certain amount of area on the sky, and so the lower edge is looking through more atmosphere than the upper edge. That's just one of many effects you have to take into account. And then the same spectrograph is used at in nighttime to look at planet targets, among other things. And here's the graph I was looking for. I don't know why it ended up here. Here is a sample of what's actually been released, available to the public, the full data set of 80,000 solar velocities. In this case, averaged to daily points for 1,400 days. And you see the scatter and the radial velocities. And if we're going to get down to things at the 10 centimeter per second level, which is the motion on the sun induced by the Earth's orbit, we got a long ways to go. So let's talk about beyond Kepler. I do need to get to TESS. Kepler provided radii for thousands of planets around fainter stars, but we really ran into the limit of what we could do for the Doppler orbit follow-up for things smaller than 4 Earth radii. And what we need to do is look at the entire sky instead of just 1/400th of the sky. Well, actually, you got 18 times better, kind of, with the K2 mission. We need an all-sky survey. So we find the nearest and brightest transiting systems with rocky planets that then you can characterize more easily, initially to measure masses, and then eventually with facilities such as JWST and giant, really giant telescopes, observations, spectroscopy of the atmospheres of the host stars during transits. And another thing that Kepler was a bit short on was the sample of dwarf stars. Actually, that was a big argument that I had with mission management. The original spec was going to be G2 solar type stars. And there aren't enough of them to be bright enough in a single field. And I argued we had to push down to much smaller stars. And you really want to move to the smallest stars because then the relative precision of your transit measurements gets better. And we did manage, well, that's actually the reason why I volunteered to take on the responsibility for creating the Kepler input catalog, because then I knew I could get as many M dwarfs as possible into that list. But we didn't do a very good job. There were only 3,000 M dwarfs in the target list for the Kepler mission. So we have completely changed that with the TESS mission. It's tens of thousands of M dwarfs that are targeted. Let's see. Yes, I have time to talk about what it takes to get a mission like TESS going. The original conversations for a follow-up mission to Kepler were in 2005. Look at that. 4 years before the launch of Kepler, we were already worrying about what we should do if Kepler proved to be successful. And those conversations were not a convention of the American Motorcyclists Association. No, the AMA in this case stands for the American Medical Association at the annual meeting in Chicago, which I used to go to accompany my wife. I like to say I was her trophy husband. And it turned out there was another astronomer, George Ricker, whose wife was also a doctor. And I discovered he was an astronomer when we got together. You know, the doctors have pretty good events at their big conventions. And it's not a bad deal. You go and work in the hotel room during the day, and then you go out drinking all the various receptions the different medical societies are putting on. And George and I got talking about what was the next step in astronomy. And I said, George, it's not high energy astrophysics. It's going to be exoplanets. And to his credit, he agreed. And so we put together a proposal to see if we could learn how to do photometry from space using an optical camera on the HEDI 2 mission that he led. Thank God it was not selected, because then we would have had to do it. And then George had this idea, look, you know, we can, and that was a $10 million proposal. It was one of these ride-along proposals. And then there was the idea we might find a big donor, be able to fork over $50 million for a small mission, a little more realistic in the cost. Guess how far that got. Nobody was willing to write a check. And then a SMEX opportunity came along in 2008, and that's a small explorer, and that was a lot more money, $104 million budget. We figured, no problem, we can do it for that. except that in the last 2 weeks before submission of the proposal, we were $30 million over budget, so we cut like crazy on the phase A. And we didn't fool anybody. They didn't choose us. But then finally, after the launch of Kepler, and we learned how important it was to have continuous light curves because of all the, it wasn't just one planet transiting in many of these systems. It was multiple transits, and it was really important to have full coverage of the transit event to get the shape so you can get the inclination accurately. And we were more successful that time and still had to squeeze to get under the cap because we had a new orbit, a really great orbit, a lunar resonant orbit. I'm not going to say anything more about that. And then we were selected in 2013 and launched in 2018. So look at that. This was a small, fast mission, and it took 13 years from original concept and conversations to the launch. That's what the spacecraft looks like. It's 4 cameras. George is the PI. I'm the test director of science. I'll show you a little bit more about the cameras in a minute. So Kepler was a pencil beam survey. It got the large number of targets by going faint. And TESS, and it could also go for a long period of time. We could monitor for 4 years. And that's where all those TTV masses came from, remarkable light curves. It's not going to happen again in the near future. And the TESS search space is much smaller, but it's all sky. And the trick is to get as much sky coverage as possible so that you can have at least a month of monitoring and a continuous light curve, and then move on to a different area of the sky. So it's a much shorter time period, and the pixels are much bigger. Instead of 4 arc seconds on the TESS, the Kepler mission, they're 21 arc seconds. See, there's a trade-off. There's only so many pixels you can fly and get the data back down. So you have to live with really big pixels. But the whole point is that our typical targets are going to be at least 30 times brighter, maybe even 100 times brighter, because they're that much nearby than the typical Kepler targets. There's some overlap. These are the really high value Kepler targets, the ones above the 12th magnitude line, because those you could do the follow-up with facilities like HiRes on Keck and HARPS North on the TNG. But it's these targets up here, and we find some of them. In fact, the very first TESS target was a 6th magnitude star that previously had been observed by radial velocity surveys. We're up in the regime where we can take advantage of existing Doppler surveys of bright targets. And immediately, now that we have a transit, look for a small planet. That's what happened with Pi Menzi. It already had a long period outer orbit for a giant planet. And as soon as we knew there was a transit, we constrained the search for the orbital motion using the photometric ephemeris, and it popped right out. That's what the spacecraft looks like in real life. Here are the 4 cameras, 24 arc minutes on a side. 24 degrees on a side. And I'll show you what the field of view looks like in a minute, but I have to show another launch because it was such a great day. The launch on April 18th, 3 years ago now, on a Falcon 9, with this enormous, what do we call it? I've forgotten the word. We're just a tiny little instrument in the middle of this enormous shield. Why did they do that? Well, this was the first flight with the big version, and they wanted to test it out. So we were on a guinea pig flight. They didn't tell us that ahead of time. But it didn't fail. And here's what the stack looks like for the 4 cameras. They're offset from each other, so you cover 96 degrees by 24 degrees, and you do kind of an orange peel in the sky. And the important point is that you get overlap coverage at the north ecliptic pole. The JWST continuous viewing zone is up here. There's another one in the south ecliptic pole. And so you get at least 27 days in these blue areas, and then in the overlap areas, you get better coverage, which means you have the ability to see longer period transits. And now that we're in the extended mission, of course, we're going back and revisiting this, the Southern Hemisphere right now. It's almost done. And picking up longer periods that way. So this is what the stack looks like. The 4 CCD cameras with 4 CCDs in each camera. And you see the large and small Magellanic Clouds here. So that the stacks are peeled off onto either side, so you can see how fantastic the sky looks when you get into space. It's diffraction limited. Well, it's got the big pixels, but the cameras, 10-centimeter cameras, they match the size of the pixels reasonably well. So here's a status report on TESS. We've been operating for 36 sectors now. I call them moons because they're not true months. They're, guess what? The lunar cycle, right? So if you go out to the distance of the moon in a very eccentric orbit, you only want to be there when the moon isn't. So you're synchronized with the motion of the moon, and the period is 13.7 days, and the moon pulls us one way in one orbit and the other way the next orbit, and it's good for at least 25 years. But it changes from orbit to orbit. The data are on the ground already for those. We're actually observing 37 now. 2,500 candidate planet hosting stars. At least half of those are false positives, very typically nearby eclipsing binaries that contaminate the target star. And a big organization, a big effort to do follow-up observations to identify the false positives and get mass determinations. And we already have 47 masses for planets smaller than 4 Earth radii in the public domain, published or posted, and many more that we know are in the pipeline, about twice as many altogether. So here's that diagram that I wanted to come back to, radius on the vertical axis and mass on the horizontal axis. Here are the 3 sigma radial velocity masses so far from TESS. And if you remember what the previous version looked like, there was only 1 or 2 targets down in here. We're filling in this region down to smaller planets because we have brighter stars, and we can do a better job with the precise radial velocity follow-up work. And now you're beginning to see that not all of them are hot colors. You know, these are cool colors at larger radii, and it's not obvious that this is photoionization of hydrogen and helium atmospheres that distinguishes rocky cores of planets that were one time built by the accretion mechanism. You know, you build a rocky core first, and then you grab a bunch of gases before the disk dissipates. And these are all of the 3 sigma TTV masses. You've seen this before, basically, because they're mostly from Kepler and K2, with one really important exception. And this is the contribution from the TRAPPIST-1 system. Really quite remarkable how this system of small planets, not too much bigger or smaller than the Earth, terrestrial planets in very tight orbits around a late M dwarf. And therefore it is possible to get the transit times of all of them and get quite accurate masses from the transit times and from the transits themselves, since the star is quite small. You know, it's the same size as Jupiter. able to get good precision on the radii. So those are terrific targets for follow-up work and are getting a lot of attention. And so I'm going to start finishing up here, but I wanted to show you what the diagram now looks like from everything that's in the public domain. So you see how we're marking out the terrestrial planets, true rocky planets, and still a lot of them are hot up in this region for perhaps historical reasons. And then populating this region up here. So it's pretty clear that a lot of these have got to have extended envelopes of light gases in order to look so big. And then finally showing you the 10 sigma masses from TESS, just to show that it's hard work to get very precise masses. But for future efforts where we want to study atmospheres of exoplanets, we really do need to know the masses, because we need to know the scale height of the atmospheres, and we also need to know something about what the sources of the atmospheres might be. In other words, are the masses consistent with models that have plate motions, continental drift, and activity of outgassing from the core or the mantle. And this is where we stand with 10 sigma masses from everything. And this is the dividing line between rocky planets and things that are, you might call sub-Neptunes or something along that line. Okay, so I'll spend the last 2 or 3 minutes saying that we're making progress towards getting atmospheric spectroscopy of planets that are rocky. It was easy to do for giant planets, enormous planets, hot Jupiters and so on, both with transit photometry, where you see the radiation from the star being blocked by the planet, and the amount that's blocked, the apparent size tells you something about from the wavelength dependence, what the absorbers in the atmosphere are. Another fruitful way is for hot planets, where they have some of their own thermal radiation, and you use time domain light curves. You watch the planet disappear behind the star and then reappear, and the small difference between the total thermal radiation is what you attribute to the planet. Diagram that was originally published by Tim Brown. Well, actually, that's the problem. He didn't publish it. He just showed it at meetings, and so it was picked up by others. I'm going to show you one result of a atmospheric study of, in this case, a TESS object of interest. One of the early, very first releases was object of interest 136, back when it could be followed up with Spitzer. And here you have the secondary eclipse. The primary eclipse over here is, you know, it goes off the bottom of the scale of the plot. But an impressive detection of the secondary eclipse, and what it shows is that from the phase curve, you're watching as the planet moves around, and you're seeing when it's transiting, you're seeing the backside. And when it goes around, you see more and more of the front side. So you see more reflected light from the host star, thermal radiation. And then the planet goes behind the star, and you see it blocks essentially everything, which tells us that there's no atmosphere, there's no heat redistribution from the really hot subsolar side around to the perpetual permanent night side. A lovely paper by Laura Kreidberg in Nature in 2019. Laura has moved on to the Max Planck Institute. So this is the future. TESS is enabling atmospheric characterization with the targets that we find. And James Webb Space Telescope will be an important instrument for the follow-up of with spectroscopy of exoplanet atmospheres, and the ELTs can do that from the ground. One of the things they can do is high resolution work, which turns out is a way of detecting lines from the planet directly. Some very nice work on bigger planets there, but that is going to be a wave of the future. For example, looking for oxygen bands on planets. Instruments are now being developed to do that. And all future missions that you can think of. We are one of the main sources of targets for the KOPS mission, for example, that is pointed at individual targets and monitoring predicted times of transits. So you really need good ephemerides if you're going to go back and dedicate time on an orbit, on a transit observation with JWST. So I sometimes like to think that this is a scientific revolution that we're experiencing, in the sense that Jacob Bernowski wrote in his book on scientific revolutions, and Thomas Kuhn then picked up and talked about the Copernicus revolution. You know, Copernicus moved the Earth from the center of the universe to an orbit around the sun. And you know, if the sun is a star, and the stars are suns, then there's going to be planets around all those other stars. And by golly, we're finding them, and we're pushing towards the place where we can study them and even see whether there's evidence that life has arisen, presumably simple life in most cases. If we're going to look for technological life, it's probably better to use SETI. So in a sense, we're working to complete, well, I guess you never complete the Copernican revolution or a scientific revolution, but we're working to complete the Copernican revolution. So I like to think of it in that context sometimes. Well, thank you for your attention. Oh, I didn't leave a whole lot of time for questions, but I can stick around.
Thank you, Dr. Latham, for the very interesting talk. So now we have some time for questions from the audience. If you joined us on YouTube, you can post your question in the comment section, and I will redirect them to Dr. Latham. So, questions?
I have one question.
Yes, please, Stacey.
Yes. Thank you, Dr. Latham, for the very nice talk. And I'm not sure if I got. Do you have a number already for the planets that TESS has detected?
The number of candidates, we call them TESS objects of interest, is, as of today, 2,487. 3 more were added last night. But quite a number of those candidates are imposters. The most common imposter is a result of the large pixels, the 21 arcsecond pixels. And there are other stars in the photometry, the light curve, because the aperture photometry covers more than 1 pixel. And all it takes is a faint nearby eclipsing binary with a really deep event to kind of look like it's a planet, because 90 or 95 or 99% of the light's coming from the target star, but all of the dip is coming from the nearby eclipsing binary. And about half of the false positives are coming from that.
And how can you distinguish these candidates? What do you have to do to?
Well, we distinguish the false positives with a big effort on follow-up work. For example, we have seeing limited photometry. We have a large group of astronomers with modest telescopes and citizen scientists, by the way, who can do seeing limited, an arcsecond or a few arcsecond photometry, and they can actually see the deep event, even with their small telescopes. And so that's a large effort. We have something called the TESS Follow-Up Observing Program, and the working group has, at last count, 440 astronomers and citizen scientists from around the world contributing to that. That also includes a much smaller number of people trying to confirm that the event is really on the target star, and we are furthermore able to measure its orbital motion along the line of sight with the Doppler effect, and that means getting a mass. You know, I don't count a planet as confirmed until I see a dynamical mass. TTVs are okay, although I didn't anticipate TTVs when I was working on writing the science section for the Kepler proposal, but it turns out it's real. And it was anticipated, by the way, by Matt Holman and Eric Agol and his student, published before it was seen. So there's, in the science section, I think we put in 2 sentences, and we might be really lucky and we'd see a system with multiple transiting planets. Guess what? They're some of the most important systems found by Kepler.
Okay,
and,
thank you.
So there's a big effort to do follow-up work, and this will go on long after the TESS mission stops functioning. We're in the first extended mission right now, but we've been invited to the second senior review. We're hopeful we'll get a second extended mission because as long as the reaction wheels are working, we're not going to run out of fuel. We got enough fuel for 50 years. Turns out we're really conservative on that.
Right.
So,
Thank you.
if it's got a dynamical mass, I consider it confirmed. If somebody shows it's very unlikely that it could be due to a nearby eclipsing binary or some other imposter, then I call it only validated. But you know, you can do that kind of validation to, well, 1%, most people do. They say, oh, well, there's only a 1% chance it could be a stellar imposter. We're going to call it a planet, and they publish.
Thank you.
Thank you, Thaisa. More questions?
Hi, Dave. A long way from the old days of the Radicon. Very impressive.
Yeah, but that was my apprenticeship. I learned how not to do things that way.
Well, well, there were other times, right? I have a question. I mean, you mentioned something about the Harvard initiative. What is it all about?
It's a multidisciplinary effort, drawing largely on different departments. Whoa, I can stop sharing. Different departments at Harvard University. For example, Jack Shostak in the Harvard Medical School has been doing experiments on the side to try to make cells in the laboratory, and he's been successful in making single cell units that have some of the characteristics that you think are required for life. And then we have people who are in chemistry, who are trying to figure out other ways that you might encode life besides DNA, alternatives to DNA, and how might the chemistry available on young planets be suitable or not suitable for the invention of life. And we have anthropologists on the team who study the history of life on Mars. And then we have some astronomers, and some of them look for planets and try to figure out what the atmospheres have in them for constituents. And do some of them have the right chemistry for Mother Nature to come along and invent life, you know, simple life to start with, but somehow get evolution started.
But is it a source of funding, or is it a coordinated effort? I mean, how does it work?
It was originally a source of significant funding until Harvard drew inside their shell. You know, they had this big science center they were building, and as of 2008, for 5 years, it was just a big hole in the ground because they stopped construction. and the money evaporated because the potential donors were suddenly no longer ridiculously rich and able to give large donations. But we survived, and we've made a lot of progress. And Dimitar and Jack Dimitar Saslov is the lead of this. You know, Dimitar can do anything. You name it, he can do it. He decided he was tired of astronomy. He'd do Origins of Life. They got a commitment from the Simons Foundation for $100 million. Not all for us. Just as, in fact, we don't get as much of it because what Dimitar and Jack do is run a team that selects promising looking projects from other institutions. And that's over, I think, several years. I don't exactly know how many years. So there's some major funding going into Origins of Life research now. And then you have the breakthrough people that are pushing SETI again. We're not part of that. I did my business in SETI for a while, as you probably remember.
Yeah, I remember that.
I've moved on.
Okay, thank you, Dave. Rodrigo.
Thank you, Nicolasi. Well, I have a question also, two questions actually. Well, you showed us that in the 1.8 Earth radii region, we have this gap that can be related to probably first generation atmospheres. But in the end, when you added the TESS data, the last data, when you aggregated it into the plot, it's somehow it look like that this gap disappears. Is that a real thing, or?
No, it's just because the gap is not at constant radius. The gap is the division between rocky planets and ones with extended envelopes.
Okay.
And that is a function of the host mass. For example, the gap is at a different place for M dwarfs. And in fact, people even think about alternate ways to make the gap in the first place for M dwarfs. And so there's a lot of interest in looking at the gap for planets on either side that are orbiting M dwarfs. And there are several systems now where there are planets both on the small side and on the big side. And so far, the gap between rocky and enveloped planets, if I may turn that into a verb, is holding up. Another thing that's happening is the dependence on the period of the host star, because that also comes into the level of insolation, the amount of irradiation hitting the planet and affecting the planet's atmosphere. And so these effects tend to smear out the simple radius valley as a function of radius.
Oh, okay.
Say
I suppose that also explains. Sorry.
Most of those early studies focused on planets very similar to the sun. So there was a strong selection effect. And as you go to different periods and different masses, it tends to smear things out.
Okay. I suppose that also explains my second question. That was the origin of all the diverse equilibrium temperatures that we were seeing in the plot. So
yeah.
You have different orbital periods.
Different orbits and different host stars. There's an enormous range of irradiation just from stellar type. Of course, we don't have very many planets around A stars yet.
Yes, that's an interesting question. How do you plan to measure the masses with such stars that don't have very much lines to get precise radial velocity measurements?
Well, how do you even prove they're planets? The first step first. An older idea from 10 years ago is you wait until they grow up, right? So you look at retired A stars.
Okay.
They become giants, and then they slow down their rotation and have lots of lines, and you can do PRV work. Well, they have some atmospheric motions that make it hard. Evolved stars tend to have more jitter. John Johnson and several others did that kind of work, working with retired A stars. But with TESS, we're finding lots of hot stars that Kepler didn't find very many of. Why? Because it has a small region on the sky. But we're getting a lot of bright stars and early F stars and A stars where they have transit-like events, and we're following them up. And an awful lot of them are false positives, nearby eclipsing binaries, which is natural, right? Because if you have an A star, it's really bright. And so there's a lot of parameter space for an eclipsing binary from a smaller star being orbited by a companion that's a stellar companion, even smaller, usually. So what we're doing now is something led by George Joe, which is Doppler tomography. It's related to the Rossiter-McLaughlin effect, where you look for the shadow of the planet crossing a rotating star. And from that, you can figure out the orientation of the axis of rotation of the star compared to the plane of the orbit. You get the obliquity, so-called. And if you see the shadow of the planet crossing the star, that way, well, you know it's orbiting the star, but then you have to do a good enough velocity to show that it's too low mass to be a star. And there's a big gap, as you probably know, when you go from the substellar limit at maybe 75 times the mass of Jupiter down to a Jupiter or smaller. And so if you can show that the mass is smaller than, say, 50 Jupiter masses, you're pretty confident that it's not a stellar companion, because the mass changes smoothly over this enormous range of masses, while the radius hardly changes at all. You know, they all have the same radius size within 10 or 20%. The realm of the brown dwarf, the elusive brown dwarf. What is a brown dwarf?
Yeah.
I'm not sure I believe it. I think it's either made like a star or it's made like a big planet, and we're just seeing the overlap of those two different mechanisms.
Yes. Well, thank you. I think if we might have a last question if Dr. Latham agrees.
Yeah, that's fine. I didn't schedule anything afterwards. My next Zoom meeting isn't until 5:30. Come on.
Okay. So we can have a last question.
Was that in the chat, or was that the pan that was still up?
No, it was Thaisa. She was the first one
yeah.
who asked the question.
Yeah. I raised the hand, but I already asked my questions.
Okay, so.
So, Rodrigo, do you have any people at LIneA who are working on planets?
Well, I myself did my PhD in exoplanets with the cohort data.
Oh, yeah.
Yes.
Well, it's a good thing I mentioned cohort.
Yeah, yes, and I had a big issue with stellar jitter, so it's an interesting problem. Well, we have people working here, yes, with not only with exoplanets but also with different techniques than transits and radial velocity, and there are people that are working with astrobiology. So
okay,
yeah,
good.
It started around 2010, and then it's being nurtured. So there are works ongoing.
Well, and you do have access to southern facilities that can deliver precise radial velocities, so you can do some of that work.
Yes. Harps and the twin, the southern harps instrument. Yeah.
Yes. Okay. Thank you for hosting me, and you're going to come visit me, Nicolasi?
As soon as I get vaccinated and I can go to the US, I'll pay you a visit, okay?
Well, you know
and
what?
I'm going to drink your wine.
Yeah, well, you're welcome to. There's more than I can drink. You know, even if I drank a bottle a night between now and 10 years from now,
you're going to continue to drink.
I have plenty over.
Okay, we should keep in touch, Dave.
Okay.
Thank you very much for coming. Okay, I appreciate it.
Bye-bye.
Yeah, okay, thank you.
Thank you. Bye-bye.
A short message for the next week webinar. We will have Tilman Trosten from the Royal Observatory of Edinburgh talking about cosmology with the kilodegree survey. So thank you everyone for attending, and a special thanks to Dr. Latham. Everyone have a great day and stay safe, and I hope to see you next week.